No. Okay, no problem.
give your remarks. Yeah. Thank you. Yeah. Thank you. Yeah.
So, very good morning to you all. Respected Principal Madam, Dr. Urpita Mukherjee of our college. Respected Vice Principal Sir, Dr. Supratim Das. The President of Physics Alumni Association, Professor Amitav Datto. Vice President, our beloved Sudip Da, Sushanto Da. Today's speaker, Professor Sudip Sinha, our colleagues, ex-teachers of the department, our beloved students, and registered participants. Today, we have gathered here to celebrate 16th Professor J.M. Dassarma Memorial Lecture. It is a prestigious event of our department. Through this event, actually, we get a scope to come in contact with so many renowned physicists of the country as well as abroad. Students also get a scope to have a very good interaction with such type of high quality scientists and get motivated themselves through these interactions to widen their knowledge. And we are trying to carry out each and every year this lecture to the memory of a legendary teacher, Professor Jatindra Mohan Dassarma. And you know, Professor Dassarma was in the department from 1947 to 1981. As Joyita already had said, he was a legendary teacher. He wrote several books, particularly the college physics. And we know during that time, there was another book, undergraduate physics, written by Ray and Dasgupta. And it was a parallel to this, college physics, also very famous book to the physics students, past as well as honor students. Professor Dassarma was very expert, in the subject thermodynamics, a branch of physics, we know. So this is the one part, educational part of Professor Dassarma. As a human being, Professor Dassarma used to come to college wearing dhuti and Punjabi, and you know, with a golden spectacle, and used to take the betel leaf with jarda. Jarda pan খেতে খুব ভালোবাসতেন, ঠোঁট সবসময় লাল হয়ে থাকতো, ডিপার্টমেন্ট সেই জর্দা পানের গন্ধে মোমো করতো, একটা আলাদা রকমের different type of experience during that time felt by the teachers and the students. He has admirable personality, and beyond that, during his time, since the days goes, nothing always good with every person. During his service period, he lost his wife and daughter, and he had some inner thought, some beliefs which cannot be explained depending upon the scientific reasoning. I got all this information from our ex-teachers of the department. I discussed in the morning and got some facts about him. I'm trying to quote only those facts. Very often, he kept himself alone. For 1 month in each and every year, he used to go to Puri and spend there in a particular hotel. This was his inner thought. I think these type of facts helped him to increase his inner strength, which was reflected in his personal life. He has such a great personality, and we are happy enough to celebrate such lecture in the memory of such a great personality. And we are trying to carrying out this event each and every year. We thank you all, and thanks Professor Sudip Sinha to deliver such lecture. Earlier, so many great scientists, including Professor Ashok Sen, was a part of this lecture. So today we are going to have 16th Professor J.M. Dassarma lecture. Thank you all. I am handing over microphone to Professor Sushant Sen to introduce the today's speaker, Professor Sudip Sinha. Thank you.
Thank you, Professor Nandi. Am I audible?
Yes.
So, thanks for entrusting this pleasant task of introducing today's speaker, Dr. Sumit Sinha. I'll begin by telling the episode when I got introduced to Sumit. It was in the early part of 2019. I was visiting IIT Mandi. And in Mandi, there is a bus service to commute between the two campuses. So during one of those bus rides between the North and South campus, I heard a young, enthusiastic gentleman speaking very excitedly about his experience of doing some experiments in a simulated zero-gravity environment. The explanation was so vivid and so captivating that I couldn't resist the temptation of gate crashing into the discussion and join the group. That's how I came to be introduced to Sumit. And thereafter, we had several occasions to meet in the coffee shop, on the aisles of the institute, here and there on the roadside. And that's how I came to know that he's an assistant professor in the School of Engineering at IIT Mandi, where he joined in 2017. Also, that he belongs to our state, did his bachelor's in metallurgical engineering from Jadavpur University, but then moved to the United States, doing his PhD from the University of Illinois at Chicago, where he later joined as a postdoc under the supervision of Professor Alexander L. Yerin, a distinguished professor at the University of Illinois, Chicago, and a stalwart in the field of electrospeeding, rheology of polymers, and heat mass transfer. Sumit is also an adjunct assistant professor in the Department of Mechanical and Industrial Engineering at the University of Illinois at Chicago now. So far, he has published more than 20 articles in peer-reviewed international journals with an H index of 12. At IIT Mandi, he is working on several aspects of heat and mass transfer phenomena, energy conversion and storage using nano architecture from polymeric materials. So far, he has been involved with 5 external and internally funded research grants and is currently mentoring 3 PhD and 5 MTech students along with 1 JRF. Apart from these, he is also avidly involved with NSS activities across Mandi town and is also a sports enthusiast, loves to write and recite poems in his leisure time. What he did not mention in this written note, that he also enjoys cooking. That I got to know during our interactions across the coffee table, and many more. But every time we met, the discussions finally centered around the zero gravity experiments. So I took that opportunity, even without consulting my colleagues at the Alumni Association, to kind of invite him to spare some time during one of his visits to Calcutta, at least a day or half a day, to come and deliver a lecture on his experience at our institute, which unfortunately so far did not materialize because of all the pandemics. But the pandemic has brought us a new dimension. It has opened up the cyberspace and the online activities, and the association has so far organized several such webinars. So using this opportunity, when our secretary, Dr. Joyita Chaudhary, told me whether we can explore a lecture from Sumit, I called him up one morning and he readily agreed. So thank you, Sumit, for agreeing to deliver the lecture at our Alumni Association. And with that, I hand it over to Sumit. So it's all yours now.
One thing, sir, our president, sir, has joined. He was facing some technical problem. So we would like to hear few words from him. Sir, please unmute yourself.
Sir, we cannot hear you. Amitabh, we cannot hear you.
I think
Some problem.
let us hold him up for the concluding remarks. Let's continue with the lecture now.
Yeah, that would be better.
সো জয়িতা তুমি স্যারকে একটু টেলিফোন করে ব্যাপারটা বলে দাও যে আমরা আপনার কথা শুনতে পাচ্ছি না, প্রফেসর সেনের সাজেশন অনুযায়ী আমরা আপনাকে এই শেষের দিকে বলার ইয়ে করব, আমরা এখন শুরু করছি, নালে উনি মনে করবেন কিছু একটা। হ্যাঁ, ওকে স্যার। হ্যাঁ, সো মে আই রিকোয়েস্ট প্রফেসর সুমিত সিনহা রায় টু স্টার্ট ইওর লেকচার প্লিজ।
প্রেসিডেন্ট স্যার থেমে গেছেন, সুতরাং আমরা শুরু করি।
হ্যাঁ, ওকে।
Good morning, everyone, and Professor Sen, thank you very much for this lovely introduction. I was meaning to tell this story, but I guess you covered the bases. So thank you once again for inviting me. And I hope I would be able to add some value to this already prestigious lecture series. So this is this talk that I am going to deliver is mostly it's mostly a story, and I hope that the students who are associated today they get to know a little bit about what lies beyond what they are conventionally studying. So I hope that during my presentation, I do believe that there will be a lot of questions that or many of you may have. I would like to answer them, but try to see beyond what is there, and it is experiments and research and everything will happen over the phase of time, over the period of time, for many aspirants like us. But how to incorporate that with I would rather say an unearthly experience, and how to experience that and how to gain insight in research, in modern research, in futuristic research. That is something that I would like to touch upon in this lecture. So let's see if you, I hope that my screen is visible. So if any of you confirm on that.
Not yet.
Is it visible now?
Yes, yes.
It is coming. Yeah, it has come.
Okay. So there are a lot of videos in it, and a lot of if you the videos will have sound, and so if you are not able to hear the sound, it would be bad for me, because that's where the fun is. So I hope that all the videos run, and then you will get a feeling of it. So the topic of today's talk, as you are already aware of, is my experiments at zero gravity. When I was writing this title of it, and I was just very mechanically writing it, and then my wife came and told me that you should make it a little fun. So yes, but the flying in zero gravity, or flying around, circling around, that's one aspect of it, but science has its own aspect. So I would like to touch upon how we integrated the thermal science over here with zero gravity aspect. So first, I will take you to my ride, to my journey. How did we come to that D-Day where this all happened, and then I will slowly get on to the fact how, why did it happen, what did we do, and then where the future can lie in regards to what we have done. So if I have to tell it like a story, and I hope that you won't mind a good story. So if I have to tell it like a story, so I have to start it like, once upon a time there were these crazy old young people in their jumpsuit jumping in joy in front of a large aeroplane, written novice pass on it, and having jumps and wearing jumpsuit written 0G ESA etc. on their suit. And if you hover somewhere here, probably you will find me jumping in joy as well, and an old guy over here, 64, Professor Alexander Yaring, who was my guide at that. So this is funny because what happened actually that took us to this point where in the middle of daylight we are all just jumping in joy like that. So that was after our flight that actually took us to zero gravity. It is not real zero gravity. It was a simulated zero gravity. We had a series of experiments that we had to do. So it's a parabolic flight, which we call it. So it's a basic physics, 10th, I think 11th or 12th grade problem. Flight moves up, it stops its acceleration, reaches to that point where the gravity and acceleration matches, and it makes a small parabola where you feel weightless. So that is so this is all about it. Now there are many countries. I mean, there are several countries, not too many. At least India doesn't have it. So I wish India had it. They have these drop towers where they take you up to 1,000 meters and they drop you from there. You get about 3 to 4 seconds of weightlessness. You can measure a couple of things, but not in an aeroplane like this. Having an aeroplane is limited. So what happened on that day? Why these people are jumping in joy? Maybe some of their experiments were successful, some of them not. So what I would like to do is to take you quickly to that day, and and slowly we'll build up on it. So this is, if I have to show it in a video, this is what happened. So nerds standing in front of an instrument flying, as you can see, it's a giant big instrument, and with a 0G flight, and me wearing a jumpsuit. But wait a second, how did that happen actually? So let me take you back, okay, onto the flashback side. So this is what a 0G parabolic flight actually looks like. Well, so it's not a real 0G, it's about 1.8 microgravity, and before that you have hypergravity of 1.8 G. So a plane actually, like over here, A310, these kind of Airbus. So what they do, they fly straight for several kilometers at a speed of 820 km per hour for 6,000 meters, and then they go up for about 20 seconds with 50-degree nose up, reach up to about 8,000 meters, and at about 685 km per hour, they reduce their acceleration and they reach that weightlessness of zero gravity or 1.8 microgravity. And about 22 seconds, they stay like that, and they come down at 1.8 gravity once again. So that means for about 20 seconds, you will feel almost double your weight. If you're standing, if you try to walk, it will be very difficult to walk. You won't be able to do a proper step, and you would feel your heart pumping really, to push blood to all the way to your brain. And then for about 22 seconds, you will feel like weightless. You will fly around, do all these different kind of things that you want to do, and then again, right away, you will be kicked into hypergravity. And then there will be a flat fly in one gravity for a few seconds. This is one parabola. And in novice space, along with European Space Agency, they used to run for about 31 parabolas per day. 3 days a campaign, and over a year they would run 3 campaigns. So we were a part of one of these campaigns in 2013 on 2nd, 3rd, and 4th of June. And on the last day, on 4th of June, I was a part of this group. And luckily for me, that was the day when most of the data were actually collected in our experiment. Well, so if I have to just think about, what is the physics, I'll leave it up to the students of this esteemed department to calculate from this problem which is shown in the left. Now, if I have to show you what actually feels like in this entire parabola, I have a small video for that. So this is what is happening at the 2 gravity or 1.8 gravity. So this guy Vladimir, he's now a part of ISS. This is not. I mean, yeah, I was used to weigh like 90 kg then, but for me, difficulty was that I was trying to push about 100 kg up. So now, so this is where I am right now. So this is like last. I am done, and then again, it came to 0 gravity, and I just flew up. I wasn't there anymore. I could not control my body. So this was it. So this is how it actually felt like. Now, when you are already inside, you don't feel like doing experiments, but we were bound to do experiments. We have spent more than 100,000 euros for just these 3 days of experimentation. So we had to do some experiments. So I will come to that. The question is that why do we need these flights? Apart from funny like this, there are many. There are many Hollywood TV serials that they have done these. Particularly they have availed these flights. In a lot of movies, they have availed this flight. So apart from recreational purposes, these 0 gravity flights have many to offer, because they are the practice ground. They are the tutorials for all these astronauts. They go up to ISS, and when they go to ISS, and they have to stay weightless all the time, they have to be trained in a simulated condition like that. One of the condition is them working inside water, in the pool of water. That is one way of doing it, just so that they can strengthen their muscle, they get the sense of time and etc. But the other thing is actually to feel weightlessness, they can either go to drop tower or they can use these flights. Now these flights give much more time than a drop tower, and hence they prefer these. Where do we use this in the research aspects? In a lot of areas. Well, I have just listed only a few. There can be many others. Well, one of the most important area is this one over here, on which I am hovering my on the cursor. So they were trying to grow spinach leaves, and they wanted to see how in 0 gravity, the growth of these plants actually happen, how they're affected. Of course, if you want, these were antioxidants, nano antioxidants, and how they actually can deliver the drugs to the muscles, and because astronauts, they lose a lot of bone mass, so how they can retain the muscle strength. So these were there. Thermofluid is one area where I was mostly interested in, and that gives a lot of flavor in 0 gravity, because gravity distorts the underlying physical phenomenon of a lot of effects. So when you have a vapor bubble growing on a hot surface, you have seen it while making tea probably. So you see these small bubbles forming, and they leave the surface. In Earth condition and in Moon condition also, this is not difficult. And these bubbles are actually a very good form of taking away the heat from very hot surfaces. But in 0 gravity, they won't go up. However, boiling on a surface is probably the best possible heat transfer mechanism that can be there, with a high scope of removing drastic heat. But in 0 gravity, that won't happen because buoyancy is not playing a role there. But in 0 gravity, what researchers can definitely study is the interface, how the vapors is moving, how the liquid is traveling around the vapor bubble, how the cold fluid is rushing down. So these things can be very well studied. Also, motor control, muscle strength, these are other areas where people would like to study in simulated zero gravity flights before going into ISS. Now, getting into ISS is very costly. It's going to cost you, millions of dollars. But if you run these experiments, simulated condition, where you can see that how less energy requirement is there in your experiment, and you can a little bit of guesstimate of how your experiment is going to run, and how the experiment can be boiled down to a very simplistic setup, so that the astronauts, who are mostly pilots and probably some engineers who are not adept in this field, they can run these experiments and can extract data. So these flights, these parabolic zero gravity flights, actually are the breeding ground for these brilliant ideas. Now, when you are in these parabolic flights, the biggest challenge is the instrument weight. For us, it was 180 kg. It cannot be more than that. And the amount of power that you can attract or you can get from the aircraft was about 1800 watt. So you have to limit all your experiment in this. Extremely challenging, but extremely insightful. Well, so now if I have to talk about the D-Day, what happened on that day. So now I give you the prelude of why we wanted to study in a parabolic flight. The basics is that my advisor, Professor Alexander Yarin, had a project from NASA, and he wanted to study the effect of nanotextured surface for enhancement of boiling heat transfer. And he had a partner from TU Darmstadt. His name was Professor Cameron Tropia, along with Peter Stephan. So they cooked up a project, and they somehow managed to get into this European Space Agency parabolic flight. So in the month of March, when I was preparing these nanotextured surfaces, my brother, Dr. Sumit Sinha, who was also in this lab at the time, he was running the heat transfer experiments, and he knew what was going to happen. Somehow I had no idea. And then I was mostly invested in developing the surface, which can actually help in maximum heat transfer. I got a call from my advisor. I went to his office. Sumit was there, and he suddenly, in his heavy Russian accent, told me, "Sumit, you are going to Germany and then France, and you are going to zero gravity flight." And I was shell shocked. I was stunned, and I was happy, elated, everything, but had a lot of fear, because I was just 1 year then in that lab. Within a year, getting that kind of opportunity was huge for me. I gladly accepted it, managed a visa, flew to Darmstadt, spent there a couple of days perfecting the instrument, and then drove about 1,200 kilometers to Bordeaux. It's a heritage city in northern France, and then for we were there for about 10 days, 7 days of pre-experimentation and 3 days of experiments. So my day was on 4th of June, 2013. And there, everybody were senior. I was the junior most. And on 5th of June, the medical team actually told me that, you cannot have, you have a lot of restrictions coming to this flight. And I said, yeah, I know. I had done easy. My heartbeat and everything is fine. My health condition is perfect. Then they said, no, apart from that, you cannot have milk at night. I said, okay, I don't like milk. I said, okay, you cannot have tea or coffee in the morning. And okay, that's going to be a little difficult because, being Bengali, we have this knack of having tea in the morning. So I said, okay, I can avoid. And then you have to be here by 6:30 a.m. for the medical examination so that you can fly at 7:30. And I said, okay, that's going to be difficult. But anyway, we are practiced in coming here at 6:30. So I will do that. And he said, don't work hard. And you have to have 8 hours of sleep. And you have to get up by 5 a.m. to be here. So I said, okay, that's stringent. And then I realized why he was making these stringent reasons. Because in our team of researchers, we had 3 Germans and 2 Indians. And all the Germans, mostly the guys, they kind of started feeling nauseating after coming back from flight, and their experience was very bad. It may sound of loads of fun flying in zero gravity, but physically it was extremely demanding. And one parabolic flight like that could drench you very well, because because the medications they give you that have a lot of bad effects on your body as well. Well, so what happened is that most of the Germans actually failed, and it was all left with one tiny small German girl and two Indians. So we got ready, we went there, and I was the youngest one. So the doctor actually gave me an extra cc of scopolamine. Now that drug is a nasty drug, because that drug can stop your bowel movement. So, and it is necessary because these 0G Airbus A310, they do not have bathroom inside, and I had no idea of it. My brother did not tell me, and he was making actually fun out of me. So they do not have any bathroom inside, and so they stop the bowel movement for that. So the food which you took cannot come down, but it can always go up, and that has happened many times before. So when we were boarding into the flight at 7:30, one of the guys over there who used to assist us during the experiments, his name was Yannick, and he told me, Sumit, remember one thing: if you have to vomit, use those bags and hold on to these bags tightly. Last time somebody actually dropped this bag and it got bursted in 2 gravity, and then the vomit started flying in 0 gravity. So better you hold on to these. I said, okay, that is fine. When I got into the flight, I could realize that I was getting a little dizzy with this scopolamine, and my mouth started getting extremely dry. The reason being is that it kind of dehydrates you. So they gave me water bottles, and the only advice I got: drink it only when you feel necessary. I did not realize I drank a liter during the entire flight, and I could realize why they said don't drink it. Well, about 9:30 a.m. the experiment started. We could not do the experiments in France airspace. We had to go to England border, and there we did the experiments. And for 3 hours, this whole thing ran for 31 parabolas. So as my job was there to record or to capture a couple of photos and videos, assist them with the compressor. So there was a large compressor inside. So assist them with the compressor because it was giving trouble. Giving them the best of the best samples, assist them with taking data, sometimes running the running the entire software, and then relieve one of them. So there were 3 of us, relieve one of them if the other person is too tired. So when the experiment started, Yannick came to me and told me, you can strap your shoes and you can stand. I thought that is the best possible way because they are experienced. I did that, and I did not realize that in 0 gravity, I would come out of that harness and would go up. And before I could scramble myself, I could get to certain place where I could hold on to something. 2 gravity started, and I fell down, and I fell down straight onto the experiment. And then I realized it's not going to be that easy. So for next 18-20 cycles, I somehow managed by holding a rod which was on my left side. But while doing it, that was a very bad proposition in 2 gravity, because in 2 gravity you could feel your blood rushing down. However, we got a lot of data. We got loads of data that we could take. In the last couple of cycles, when the experiments could not be done anymore because our compressor completely failed, I went on to, I was one of the few who could go to the cockpit and could sit with the pilot and see what they actually see during these flights. And I thought that these pilots would be very serious, but they were actually making fun of each other. Also, in a couple of times, I could go to the back and could do these, push-ups and, flying around. And of course, I would show you these videos. At about 1:30 to 2 p.m., we came back. By that time, due to over-chewing for a couple of chewing gums, my jaws were hurting badly. But then one of my friends actually, one of the German guys gave me a baguette, a French baguette. And a French baguette is those kind of breads. You can take it with a sketchy neighborhood and can beat anyone up with those breads. So it took me about an hour and a half to chew on to those baguettes and finish it. After that, it took about an hour to wrap up everything. And by 5:30, we were back at our villa in Borjo main area, and we partied hard. Well, we got the maximum data on that day, and this was our day. And we were really happy because out of 12 groups which were there were only 2 who could publish their data, and maximum of the data came on that day. So when we so this was the experimental setup actually. So this large giant instrument was that. The principle was it that this is a heater which could go up to 600 degrees in 5 minutes. In 5 seconds, and we would be mounting a small sample on this heater, which is shown over here where my cursor is, and we'll be controlling its temperature. And one drop of liquid will fall onto the surface, and that droplet we would be able to see, and this is the droplet generator chamber, and we'd have a high-speed camera to see it, and we have a small we have a small compressor over here, and the entire circuitry is within this setup. So he's Professor Alexander Yaren, and this instrument was his brainchild. So this what happened during the experiment. So these are small videos. There were a lot of decision makings that happened during the experimentation, and there was one small funny weird thing that happened, and you may end up laughing at the end as well. So this was one incident. So on the background, as I run this video, on the background, if you're able to hear, what happened when you are getting into this 1.8 gravity, they say, pull up. So that means they are going up now, and then they will say 30, 40, and then injection. That means that goes into this 0 gravity, and then they will say pull out. That means now they are pulling out from the parabolic, the 0 gravity area, and then twice gravity starts again. And you could see immediately people reacting to that. So he said pull up. Now you will hear 40 and 30. And you heard injection, and you hear this sound, hissing sound at the back. Everybody is flying right now. So now the decision making is when to turn on the compressor, when to generate that drop, at what frames we should be choosing to understand that. Now you hear in the back 30, 40, and then pull out. So this is the time actually in this video, you see me taking a video from the, from below, because I fell down and I could not get up into gravity. So I could just raise my hand a little bit, and I was filming that video. So this is one of the other incidents where in one of these incidents, I actually kicked a Japanese professor at the time. So this is the compressor over here, and this is the droplet generator. So again, these decision makings and everything over there. And this is where I decided to have a little bit of fun. So you can see this guy, just standing upside down. And I beg your pardon for this part, but these are all first for me. Well, that felt like a flying duck. Well, when we were not doing the experiment, I'll just skip a little bit to that. So this was one of the very few last cycles when we were allowed to go to the back and have a little bit of fun. for a very brief microsecond, you could actually feel that you won't be able to control your body. So this guy at the back, he was already doing a couple of days, so he were more or less familiar with it. I was afraid, so I was holding on to this rod. And now then the pull-out comes, and we have to get to a point where we should not move that much. Also, if you try to move, this will hamper your motor stabilities as well. Okay, so the question is now coming to the business end. What did we study? Well, we actually studied spray cooling of high-power microelectronics in zero gravity. As Professor Sen was mentioning that a lot of discussions happened on cooking. So I was a little bit of cooking enthusiast at one point of time before I got married. So those who cook and those who don't even but see them, you'd see that if your frying pan is really hot and you try to put one droplet of water onto your surface, you'd see that the droplet, runs away from the surface. That phenomenon is what we call it as light and frost phenomenon. That is the point of minimum heat transfer in the boiling regime. Well, that happens because the evaporation takes place so quickly that majority of the droplet sits on a vapor pillow and it hovers onto it. And whenever the area where pressure is less, it moves to the direction and leaves the surface. What we wanted to study is, can we reverse this phenomenon? So in one of the cases when, in these two cases where one individual droplets we could hit onto the surface, so this was a smooth bare copper surface, and this was one of the nanotextured surface, we could actually see that in this case, in the second case, we could remove double the heat from it, despite the fact that it was all in zero gravity. So taking the droplet, reaching it onto the surface was the most difficult part. And not only that, reaching to the surface and pinning onto the surface, which was otherwise difficult anyway due to very high temperature, shows the efficacy of that surface itself. Now, the question is, why is this happening, and why suddenly we want to invest so much of time in studying these heat transfer phenomena? The reason was, our motivation was for microelectronics cooling. So now if you see these pictures over here, every one of us like the idea of automation. Just think about it. There are about 80-90 candidates who are seeing it. The data, all this data that we are generating is being processed somewhere else. And not only our data, there, in that place, in that somewhere, in that area, in that shaded area, which is running under air conditioning, etc., billions and billions of people's data is processing. So when you process that much of data, you run a small computer, you work on, you play a little bit of game on your laptop, and you see how hot that laptop gets. Your cell phone gets hot so much. We like these automation. So just think about when billions of data is processing, the amount of heat that can be generated is drastic as well. Just think about an UAV which has to fire a missile, and that contains a lot of microelectronics. And in that, there will be a lot of power electronics which would be generating temperature as much as 140, 150 degrees centigrade inside the component. And that heat has to be dissipated out as well. Well, the problem in modern world is that we are increasing the number of transistors every now and then, but our clock speed is somewhat limited. That means the calculation that we can do is somewhat limited at the speed of it. But we are all doing it at the smartphone level. By 2016 itself, we are at a smartphone level. So that many billions of transistors in an integrated circuit. So that produces tremendous amount of heat. But processors has gotten smaller. Every now and then we need, light, compact laptop without a bulky fan inside. And then heat transfer has to be efficient. There is a certain called TDP, thermal design point, which actually shows how much heat can be dissipated. Your regular i5, i7 laptops are rated for about 90 watts. A gaming laptop can well go up to 300 watt of heat that needs to be dissipated. Now, with a simple fan, this amount of heat cannot be dissipated, especially given the fact that these laptops, these modern day computers, they have circuit features which are not only just 10, 14 nanometer. These days, these are 10 and 7 nanometer, and very soon we would be getting 4 nanometer. So which means they are much more compact and producing large amount of heat, and that has huge implication on your battery. The microelectron and these microelectronics consume as much as 4% of the net electricity that is required in any country. So the smaller the chips, the hotter they get, just simply because of Joule's law of heating, and majority of the PDAs fail because of this thermal reason. And this is one of the reasons why people assume liquid cooling is one of the best possible cooling technique, where they just take the entire rack of the GPU, they put it inside liquid and let the liquid boil off and take the heat out. Now, however, in zero gravity, as I mentioned previously, boiling is one of the best possible techniques to take out this heat. In zero gravity, however, that does not work, because in gravity condition where these bubbles, which you can see on the bottom image, bottom left side, they can rise up. So they initiate nucleation of a vapor bubble. The bubble grows, they take out heat, and they leave the surface. But in zero gravity, they do not. However, boiling is still the most efficient heat removal technique. So in order to understand the process, there are several researchers who have spent many days working on it. One of the researchers, Paolo Di Marco, along with Peter Stephan, they experimented on a setup in Ruby at ISS after 10 years of exploration. And this is one bubble they generate on the surface, study the interface phenomenon, and then because of absence of gravity, they pull this droplet with a high electric field, and thereby they try to understand the cooling phenomenon used with boiling heat transfer. Now, so our solution in this matter was that not the entire microelectronics is hot, right? So they have the hot spot. So what if we issue a single droplet onto the surface and allow it to boil on the surface, but the most important question was to stick onto the substrate, and then just cool that area. And once one droplet evaporates, next droplet will come, or we can have a jet onto the surface, and in that sense, the net heat removal in terms of watt per centimeter square would be much higher. So in this regard, my job was to develop these kind of surfaces. Okay, so the idea was that you have this GPU, you place a copper plate onto the hot spot, and where the copper plate would be textured like this. These are what we call it as metal plated electrospun polymer nanofiber. Earlier in one of our studies, we had shown that these electrospun polymer nanofibers can reverse the light and frost effect by wicking the droplet inside the surface when the droplet is coming with a certain velocity potential, and it hits the surface. So as it hits the surface, it goes inside, wicks it, and cannot come out. And once it tries to come out, it chops the bubbles as they try to come out. The question is how to easily manufacture this. One of the easier solutions of doing it is by electrospinning. If you are interested, I can explain the phenomenon of electrospinning in details. However, the basic detail over here is that there's a polymer solution that is being pumped through a needle, and this needle and one of the collector, they are being electrically connected with a very high voltage supply of about 10 kilovolt. And a polymer solution, when it comes out from the needle, it gets attracted, overcome its surface tension, and gets pulled out as a viscoelastic jet. And that jet over time solidifies and goes through several bending instabilities, and it gets collected as fibers. Okay, and these dry polymer fibers are then metal plated to, so these are just age-old simple electroplating technique. The only way is to tweak the structure in such a way that it mimics a kind of thorny devil structure. So these thorny devils, are these, these are dragon, I mean, they are called dragons practically, but they are not. So these are lizards which have these spikes on their back, and these spikes actually help them to get the moisture from air, from arid atmosphere. So these spikes, they are hydrophobic in nature. They are hydrophilic in nature, and they allow nucleation happening on them. So the same structure was tried to be mimicked over here, and in normal gravity condition, when we tested at 150 degrees centigrade on bare copper surface, where the droplets tend to splash, and they tend to make these different kind of bags formation on the surface in the light and frost. The nanofiber surface with metal plating actually allows wicking and enhanced heat removal. Well, so during our experiment, we had these two conditions. As you can see over here, so this is in 1.8 gravity, when droplets were coming like a jet, and we had about heat removal rate of about 128. However, in zero gravity, we could remove about 190 watt per centimeter square. And you can see that this entire situation was very difficult to issue one droplet on a particular spot, and that is one of the reasons why some of the drops came at different locations as well. While studying it with a high-speed camera, we could, and you can see how this is boiling, and it's not leaving the surface anymore, and it has been pinned onto it. It is not bouncing back and flying away. And in ground condition, we could remove all the way up to 600 watt per centimeter square. In zero gravity condition, we could remove about 190 watt per centimeter square, and that is one of the highest data that has been obtained for zero gravity conditions also. So this is what we did during our experiment. Now the question is, what else can be there? Okay, so there are many other things that can be studied. This is what we have been trying to do at IIT Mandi in our lab. This is one experiment, what we call it as swing boiling. So since bubble has to leave vertically for the buoyancy to take place, we had this condition where the bubble is leaving from the surface normal to it, and hence buoyancy does not play any role. This is a self-actuating motion governed by the nanotextured surface on a particular heater, which is being on and off as it gets hot and cold, and then it swings in it, and it moves into the liquid, and it kind of dissolves all the bubbles that has formed, and then delay the vapor layer formation that generally happens in zero gravity. This is a similar kind of experiment. You can see the bubbles are leaving from this side, and it is moving towards the other side. Now it has switched the polarity, and it is moving in this direction with a vigorous bubbling. This bubbling was enhanced by the presence of this nanofiber texture. Now, at the same time, if I show you this video, this high-speed imaging, this is a superheated substrate where an ethanol drop was hitting, and you can see that it kind of spreads out, boils immediately, and then there is a lot of atomization that is happening, and then eventually they form a couple of these big droplets, and these droplets over here, they tend to run away from the surface, and this droplet stays as it is. It is not changing its volume at all, and it is trying to go towards the edge where it can leave. On the other hand, if we have a textured sample like this, where we mimic all these cold hot spot, and we put these texturing on it, and I'll just skip a little bit, and you see that these droplets over here, where earlier these droplets have left, these droplets over here got pinned, and they cannot leave the surface anymore. Thereby, we use the entire potential of these nanotexturing in terms of heat removal. So these portions have been boiled, and this droplet cannot leave the surface anymore. So with this, I would end this presentation. So there is no thank you, there is no conclusion slide or anything, because there is no conclusion to draw. Zero gravity has a lot to offer, and zero gravity experiments have a lot to offer, and as I have mentioned, that these experiments are practically, pathway to International Space Station, and I believe, with time, our students would get a lot of these, would take or would derive inspiration out of these, and would be able to go beyond and do the experiments, okay, and would make their own mark. And I hope that very soon in India we'll get to see these kind of experiments happening as well. With this, I would like to end, and thank you very much for listening to me. I hope the videos ran and you were able to see them. Thank you.
Thank you so much, Professor Sinha, for this wonderful lecture. It was a great experience. Thanks a lot. Now I request Dr. Pradipta Kumar Mondol to conduct the question answer session. Participants, please type your questions in the chat box.
So I hope, Professor Sen, I was able to deliver the exact things which probably you were not able to get the entire picture of that day. I hope I was able to deliver the entire picture of that day.
Yeah, it was very nice. Although I had a few interruptions during the course of lecture because of the network problem, but overall I could understand it.
Okay, thank you.
Because being in the microelectronics field, I'm aware of the problems, so I could sort of fill in the blanks.
Okay, great.
Myself, Pradipta Kumar Mondal.
So,
All of you hear me? Am I audible?
Yes.
yes.
Okay. Konal Pathak asked the question that could you explain the phenomenon of swing boiling in more detail?
Well, definitely I can. So I have to go back to the presentation, if it is okay. So let me show this. So this, so what was there? So just think about it. When the bubbles leave the surface, it happens for the cases of metal quenching, and in those cases, generally you see, or even you have probably seen, during cooking actually. So your oil is really hot, and then suddenly one spice jumps out, right? Because one small droplet of water or small droplet of oil is just bursted because of the presence of that. So the force with which the bubble leaves the surface is actually drastic. It's quite a lot. And what we actually did, we had these two heaters, put in this dimension like that, or sandwiched together. Okay. So once we have sandwiched together, and what we did, we switched the heating polarity. So either we heated this surface or heated that surface. And once it was heated, the bubbles which were leaving the surface, they leave vertically first and then they go up in gravity. If it was like this, they would just go normally up. But if that sample is kept vertically, then the bubble will always leave normal to the surface. Now, as it leaves normal to the surface, all these thousands of bubbles that leave, they push the surface back. Now, in zero gravity, the condition is that you have to remove the bubble. So now what if the surface doesn't stay at its position, the surface tends to move back, and then automatically we end up mixing the liquid. And that is what happened when we were having boiling on this surface, the surface moved to the other side, and vice versa. So this was the underlying phenomenon for this case. So we actually got a velocity. I can very well share this paper with you. We actually realized that this has this pendulum kind of a motion, and our prediction was about several centimeters per second, which was at the same scale of the actual experiment. So I hope this answered Mr. Pathak's question.
Okay. Hello.
Yes.
Yes. Thank you, Mr. Sinha. Another question is there. Dibbo asked that what could be the efficient possible local heat removal technique to be applied in finite gravity?
In finite gravity. Well, so the thing is that there is no better technique than having phase change heat transfer, right? So if you are, suppose you have water and you are boiling it, just think about it. You can take several kilowatt per centimeter square of heat from the surface. That is the best possible technique. The problem is that you cannot have water. You can try having double distilled deionized water, but that is not possible. Still not possible because of some debris. Somewhere it will come and then it will short circuit it. So for these kind of setups, people have tried to come up with fluorine-art fluids like FC72. This is old, but new fluids are like Novex 7300 or Novex 7100. These are, they do not affect the ozone layer. They're more or less bio-friendly, but they have less specific heat capacity and lower evaporation heat transfer. So apart from boiling heat transfer, the other best possible technique is having this spray cooling. If you have a pool of liquid boiling, other than that, you can always go for jet impingement or spray impingement on a surface, like the exact thing which we have shown in my talk. The other way of doing it is by passive cooling. And if you just Google, you would probably find liquid cooled temperature, where they actually run water behind these highly heated microelectronic components or these integrated circuits. So that is one easier way of taking out heat. But with this, you are limited somewhere at the range of 100 watt per centimeter square. And you cannot really hit 1 kilowatt per centimeter square.
So
Thank you, Dr.
Actually,
Sinha.
Dibbo Shankar has too many questions. Dibbo Shankar, can you unmute yourself and ask questions? You have more questions, I think.
Yes.
Yeah, can you hear me?
Yes.
Yes.
Yeah. So my other question was why the nanostructure on the surface should be like the fiber you showed. I think to imitate the lizard skin, nanorod will be better to imitate lizard skin, right? Why you are sticking to?
Yeah, definitely. See, the point is that having the nano architecture with a protruding structure was the most important point, right? Now, the thing is that you would like to minimize the cost of it. And electrospinning was a very simple technique. And then, this is a user-friendly technique. And then all you have to do is to electroplate it. Electroplating is it does not take too much of too much of price. They don't put too much of price onto this aspect. Whereas you want to grow these nano architecture, nano rods, you do it by PVD or CVD or by atomic layer deposition or something like that, or MBE. These will be always costly, right? You would not like to add cost to it. Now the thing is, if you have this droplet coming at a certain velocity of say V, and then you have this wicking structure there of this nanofiber, what happens is, suppose you have a droplet of about 1 millimeter hitting a pore of about 1 micron, then the velocity increases in that pore, with a ratio of 1 millimeter by 1 micron. So about 1,000 times the velocity potential, the impact potential increases, and that allows it to wick into the structure. Now, apart from the fact, what also happens is that because of these architecture, you're overheating of any droplet that nucleates or grows happens. So suppose you have this surface and you have a pool of liquid on top of it. So you can have this liquid at a temperature T1 and the wall temperature is some T2. The droplet which is developing on this surface has an average temperature of T1 plus T2 by 2. But if you have this architecture which are metal plated, this architecture will also have the same temperature as T2. And then your droplet and the average temperature of the droplet will be even higher than the previous case. So this was the reason for, and if it is more higher temperature, it is easier for it to leave the surface as well. Especially this happens in the nucleating boiling heat transfer. So, so this was the reason. Now, you want to have nano pillars like standing like this. Yes, that can very well help it. But if you have to design this nano pillar in such a way that you don't end up having a lotus-like of a structure where droplet just levitates on it. It should be able to wick into it. And that's where these nanofibers were cost-friendly, inexpensive, but easier to use. I hope I was able to
Thank you,
answer.
Dr. Sinha.
Yes.
Another question is there, Rupam Saha.
Yes.
In microelectronic devices, can we create such zero gravity situation as of now? If not, where are we standing currently to apply such amazing zero gravity in physics and electronics?
Well, well, the thing is that the first line of the question probably was not right. So you want to so zero gravity is a condition. You want to use this for microelectronic devices. Yes. So see, the semiconductor devices will run like they run in zero gravity, like they run in normal gravity condition. So they will be same. But the problem, what will happen is the heat that the amount of heat that will be generated here and there, they will also be same. In terms of cooling it is the question. Now there is one more, especially probably this will be of interest for physics students, creating a defect-free single crystal. Now it's not that difficult. It is not that easy in creating in normal gravity condition. In zero gravity condition, the idea was that it would be very easy to grow onto it because there is no disturbance, there is no perturbation that is happening. Unfortunately, people have seen that it is not that easy. I guess Professor Nandi would be able to shed some light onto it as well when we were discussing about it yesterday. Because of a lot of disturbances that happen, disturbance from the pump, disturbance from the entire system that is vibrating, these these frequencies, they affect the nucleation and growth. So under a very stringent condition, you can expect some dendritic growth in a particular direction, perfect defect-free crystal as big as possible in zero gravity, and probably that is where in electronics industry we may see a lot of changes happening. But other than that, cooling microelectronics in zero gravity is still a big challenge, especially the fact that the side which faces the sun goes temperature as high as 150 degrees C. On the other hand, it is as low as minus 40 degrees C. So, there is a wide temperature region. Protection of these microelectronics with a lot of these heat resistant technique is going to be the crucial part in this research.
Thank you, Dr. Sinha.
Professor Roy, Odito, 1 minute. Professor Roy, may I ask you
Yes.
one question, rather maybe suggestion?
Yeah.
We know that in such cases, the heat flow is governed by the Reynolds number and Prandtl number.
Yes.
In computational fluid dynamics.
Yes.
So, is there any experiment which have been carried out in zero gravity environment just to study the effect of these two numbers, Reynolds number and Prandtl number?
Exactly. So this is one domain I did not touch, and I would like to leave it to the imagination and the inquisitiveness to the physics students. Is what we call it as flow boiling. So where the liquid actually flows in a microelectronics in a microchannel actually. So to answer, it is the answer to the same Dr. Pradipta Kumar's question was that how to incorporate these cooling techniques. So one of the cooling technique is you say, suppose you have this microelectronic and you have a backplate, which is on this side you have all the electronic chips, and on the other side you have
Sorry. Okay.
So on this side you have the microelectronics, all these circuits and everything, and on the back side you have the electronic. You have a heat sink. Now on this side, what you can do is you can have a small microchannel engraved over here, through which the liquid can flow. If the temperature is high enough, the liquid can actually boil. And in those cases, the effect of Reynolds number and the Prandtl number can be very well checked. Definitely, you would not like to have liquid metals inside. You would rather like to have some fluid which has sufficient enough of Cp so that the MCPDT can be used efficiently. Now, the effect of Reynolds number, you increase the Reynolds number in a microchannel, it's very difficult to get turbulence. So you won't get turbulence. If you can get turbulence, then your heat transfer will be much more efficient. But what will happen that it will create too much of pressure on your pump, and you will have a lot of pumping pressure loss, and that will add to your already present energy requirement to run the entire system.
Right.
So rather, you would like to have a self-sustaining, self-actuating mechanism. But however, the same group, Paolo Di Marco and Peter Stephen with Cameron Tropea, and I believe one of the professors' name I forgot, they have tried, seeing also Isam Mudawar and Suresh Garibella, they have did it with NASA for flow body.
Thank you.
Yeah.
Pradipto.
Okay. Thank you, Dr. Sinha Roy. Another question from Ramesh Raja Khan.
Yes.
We know that hydrophobicity is combined with atmospheric pressure. But does the zero gravity have any effect on hydrophobicity?
Well, ideally, it's not going to happen that, because see, the point is, if you're just talking about International Space Station, you still have a bit of gravity there. But anyway, the pressure has nothing to do with it over there. It's the cohesion force, or it's practically the polarizability effect that comes into play of the surface and the liquid and the liquid molecules. So in zero gravity, it should not play much role. However, if we want to check whether how in zero gravity hydrophilic versus hydrophobic surface can assist in generating bubbles, yes, we may see a little bit of effect there. In hydrophilic surface, these generation would be much easier than in hydrophobic surface because of the wettability issue, and that has nothing to do with zero gravity.
Thank you, Dr. Sinha Roy. Another question is there. Konad Pathak asked, microdroplet optics has certain challenges because of its deviation from perfect spherical shape under normal gravity. Is it realistic as of now to expect such experiment under zero gravity?
Well, yes. The point is, if we want to focus on a perfectly spherical droplet and see the interface and growth pattern or contraction pattern, etc., yes, zero gravity assists in a lot of it. But at the same time, actually, during when I was the part of the zero gravity experiments, there was one group who was trying to create black hole. So he had this droplet, ferroelectric droplet, and they wanted to squeeze it spherically, symmetrically to one small droplet at a single point, and to see how it creates a black hole. Of course, the theory does not lead to that. There will be always some disturbances that are there even in the so-called zero gravity situation, especially if it's aimed for space stations and all these parabolic flights. The fingering effect will create a little bit of distortion because of the difference in viscosity at the surface level. So we probably would see the best possible spherical droplets in zero gravity, but not entirely sphere. That is my understanding. That is what I have seen myself as well.
Thank you, Dr. Sinha Roy. There is no more question, and I am transferring my conversation to Dr. Joyita Chaudhary.
Thank you, Pradipto. Now it is the time to bring the curtain down. Before that, on behalf of all the participants, a big thanks to Dr. Sinha Roy for sharing his great experience with us. Thank you so much, sir, for readily accepting our invitation. Thank you for taking us to the zero gravity environment virtually.
Thank you. I'm honored, actually.
Okay. Thank you to all the participants. Thanks to all the participants for registering in this program. I am grateful to college authorities, especially Principal Dr. Orpita Mukherjee and Vice Principal Dr. Supratim Das, for the support they provided in the arrangement of this webinar. Whatever we have done today came to this shape because of continuous guidance from the President of Former Students Association of Physics, Dr. Amitabh Dotto, Vice President Dr. Sudev Bhattacharya, Dr. Shushanto Sen, our head of the department, Dr. Upendranath Nandi, and treasurer, Dr. Shatodal Bhattacharya. Tremendous efforts of my other colleagues, Pradipto, Joydeep, and especially Shushovan made it possible. And last but not at all the least, students of the department. I will not say thanks to you. For every need of the department, you were there, you are there, and I believe you will be there. And this tradition will continue in the Department of Physics. As Secretary of Former Students Association, I am taking the responsibility of all inconveniences faced by the participants in today's program. Thanks to the participants again for patient hearing. Stay safe. Hope to meet you soon in a real meeting, not a virtual one. Thank you.